Thank you very much. 皆さん、こんにちは。ご来場ありがとうございます。
めっ
Okay.
ちゃ嬉しい。
ちょっと
ありがとうござい
だけ
ます。
話すことができます。
素
So I'm
晴
going
らし
to
い。
speak in
素晴ら
English.
しいっすね。
In English.
めっちゃ嬉しいです。
Unfortunately, that's most of my Japanese, so we're going to have to do
No,
this
no,
in
no, no.
English.
I'm so glad to hear your Japanese talk. Yes. Thank you so
Yeah,
much.
just I'll try to speak slowly and clearly. Sometimes I might get excited, so if I do, slow me down, let me know. Yeah, and we can take it at your pace. So as you can see today, we're going to talk about singular learning theory for alignment and AI safety more broadly. I'm excited to talk to you about all of this today, especially because singular learning theory is from Japan. So it's good to come full circle back. Okay, so we know why we're here. I think most of us understand why we're here. It's because AI is moving very quickly. And we have this sense that we could get transformative AI systems in the near future. As soon as 2 years away, maybe 20 years away. In any case, probably in all of our lifetimes. And one of the main reasons we expect this is true is because of the scaling laws. So starting in around 2020, although there's also earlier work from Baidu, we discovered these scaling laws where increasing the amount of compute you train on, increasing the amount of data you train on, increasing the size of a model, reliably improves performance in neural networks, as quantified by these scaling law exponents. So from this, you can get this sense of certainty that if you're going to continue this process, if you're going to continue making these data centers bigger and bigger and bigger, and training on more and more data, the models are going to get better. Right? So that's one of the reasons we're confident that this prediction is going to bear out, is that models are going to keep getting better as we make them bigger. At the same time, there's this other observation, which is kind of in tension with this first observation. And that observation is of emerging capabilities. So predicting performance on specific tasks is difficult, right? It's hard to predict exactly when a model is going to get good at mathematical reasoning or being able to prove certain formulas. Maybe handwriting recognition at some point was difficult. And the problem is that even though we have this reliable prediction of smooth scaling overall, on specific tasks, we don't know what's going to happen. And so there's a lot of uncertainty here. We don't know exactly how AGI, artificial general intelligence, will look. And that means that we're dealing with a lot of uncertainty, and things could go badly if things go in an unexpected way. Most importantly, we're not ready. Okay? We're not ready because the current techniques we have for aligning models are not enough. For one, they're very fragile. So here's an example of Bad Llama, where they take an open source model that's been safety fine-tuned, it's supposed to be safe, and it's very easy to get it to produce harmful text. For only a few pennies, for only by training on a few samples, you can actually get this model to lose all of its safety training and start producing harmful material. Okay, so our alignment techniques aren't deep in a meaningful sense. At the same time, they're pretty shallow. So even a model that has been made safe, you can usually prompt it in a way that you jailbreak it, and all of a sudden it's telling you how to build a Molotov cocktail. And this is SIGNET. SIGNET was supposed to be the state-of-the-art in safety, and it was broken within a day of release. Right? So these techniques we have, not quite enough. And maybe most worryingly, alignment techniques currently don't seem to be enough. So there's this example from the Sleeper Agents paper and by work on alignment faking from Anthropic that shows that models can keep capabilities that we would like to remove from them that don't actually get removed during this alignment process. So somehow we need more ideas. We need more powerful techniques for actually changing the values in a meaningful way in these systems. And that's why I think this picture is actually a very accurate representation of where we are with AI systems today. Okay, so in this talk, I want to talk about singular learning theory as a basis for developing a science of alignment, a science of developing not just a better theoretical understanding of how to put human values into these systems, but also how to develop the engineering practice of new tools that let us actually implement this. I'm interested in questions like, how do you understand generalization? Why do neural networks generalize as well as they do? And how do you interpret internal structure? What kind of structure is there inside of neural networks? Can we understand this fundamentally? At the same time, can we develop new measuring devices that predict generalization and that tell you about what's going on inside of a model? And can you actually use this to steer models to be more reliably aligned with humans? Okay, so what we're going to do is follow this in three parts. So first, I'll give you a bit of a background on singular learning theory, go through some of the basics, and then we'll talk about a few problems in alignment from the perspective of singular learning theory. We'll show that maybe questions that are currently quite vague and insubstantive can be made more precise using this formalism. And finally, we'll look at a few examples of SLT in action, what SLT applied to real-world systems looks like, results from the last few years, from me and my collaborators, especially in work going back earlier. Okay, so SLT in theory. How does it work? What is singular learning theory about? Well, I want to come back to this picture, to the scalar laws. Sometimes when you find yourself in a weird situation, it's a helpful exercise to ask yourself, how did we get here? And I think that the answer is that something right around this point changed. Around 2012, 2013, deep learning started to work. Okay. Empirically, just all of a sudden, we found that the classic bias variance trade-off broke down. Classical learning theory predicted that making models bigger, training them for longer, would cause them to overfit, that it would lead to actually a degradation in performance. But this turned out not to be true. Simply by making models bigger, training them for longer, we got reliably better performance. Okay, so we're in this weird new territory here, where a lot of classical learning theory didn't expect us to end up in this point. And the results from the subsequent decade of making models bigger and bigger has showed that this continues to be true. Okay, so deep learning works. That's empirically the result of the last decade. But that's not really a satisfying answer. So let's go deeper. Why does deep learning work? Well, I think the answer is that deep neural networks are able to learn algorithms. So let me give you a few examples. Here's an example from GPT-2 small of a circuit inside of the model that researchers found that performs what's called indirect object identification. It's a specific linguistic task where you're trying to find the right next word in a particular kind of problem. I'm thinking of the example of grokking, where researchers and others found exactly what the model is doing inside. And so you can analyze it in terms of transforming your problem into a problem in a Fourier basis, performing some kind of rotation, and then transforming back. So we understand that there's structure inside of this model that you can see visibly. And even earlier examples where vision models compose features hierarchically from low-level features up to higher and higher level features. So you compose a car detector by combining a window detector with a car body detector and a wheel detector. So in each of these cases, what the neural network is doing is it takes the data, it constructs some rich representation of that data, and then it computes on top of that data in a systematic way. There's hierarchy, there's sequential processing going on. This is quite unlike earlier kinds of statistical modeling approaches. A technique like linear regression or Gaussian process or clustering, these techniques don't have the flexibility that deep neural networks do. It would never be possible, for example, to ask one of these older methods to learn how to sort a list. Whereas a neural network can learn how to sort a list and do many other kinds of things at the same time. So neural networks have this hierarchical internal structure that's flexible, that can be adapted to the task at hand. And it means that they can adapt the transformations they're implementing to whatever's necessary for the data that they've been trained on. Okay, so maybe algorithms somehow hold the key to what's going on in neural networks, this ability to flexibly learn different algorithms. But now we get a deeper question. Why? Why is this even possible? How do neural networks learn these algorithms? What are these algorithms really? And here, I think we're getting to one of the core questions at the heart of AI research more broadly, and AI safety in particular. That's because questions like what is the nature of learned algorithms have both this scientific and alignment relevant impact. The question of why are neural networks able to learn algorithms at all is related to the question of why do they sometimes learn the wrong algorithms, right? Can we prevent them from learning the wrong algorithms? Where do algorithms come from? Similar to the question of where do goals and values inside of these systems come from? Goals and values seem to be just another kind of algorithmic structure. What kinds of algorithms do neural networks tend to learn? It's a very similar question to what is instrumental convergence? Do models trained on different kinds of problems often learn the same subgoals, the same subroutines? What are these learned algorithms? It's a necessary problem to answer if you want to do interpretability in a reliable way, if you want to understand what the model is doing inside of itself. And maybe the question of how do these algorithms form is very much related to the question of how do you align models in practice? How do you steer the learning process so that models end up with the capabilities we want? The problem is that this is a perfect question for learning theory to answer, understanding the nature of learned structure. Unfortunately, classical learning theory is not equipped to handle this problem. And that's because classical learning theory makes an erroneous assumption. It assumes neural networks are what are called non-degenerate. What that means is it assumes that the loss landscape of these models looks like the left-hand side of this picture. So somehow what we're doing during neural network training is we're walking down this landscape and trying to find the lowest point in this landscape. It assumes, classical learning theory assumes that a small perturbation to your final weights will always increase loss. You're in a basin. In fact, you end up being in the right-hand side of this picture. So neural networks and other systems like them have what's called degeneracy, where you can change weights without actually changing the function being implemented, without changing the loss. Now, because classical learning theory is wrong, or it doesn't apply to neural networks, it turns out a lot of results from classical theory do not apply to neural networks. That puts us in a weird position. What can we do about this? Well, fortunately, this is the starting point of singular learning theory. I think the simplest definition or explanation of what singular learning theory is that it's a relaxation of an assumption that's wrong, incorrect in the classical theory. So singular learning theory asks, what if you actually account for the fact that neural networks can be degenerate? What kind of theory would you construct then? And that's indeed what you get with SLT. And in fact, the problem isn't just that we have to deal with degeneracy, but singular learning theory suggests that this might be key to understanding many properties of neural networks. Maybe this degeneracy, you can change weights without changing the function, is actually deeply tied to the ability of neural networks to learn algorithms, to flexibly adapt themselves to the world at large. That's because, in a sense, learning different algorithms requires different patterns of degeneracy. So that flexibility, the algorithmic flexibility, shows up as flexibility in this other sense. We'll look at exactly what that means in a few examples. So maybe the deep idea of SLT that we'll explore here is that geometry might be key to understanding neural networks. And the properties of this loss landscape are fundamental to what's going on inside of neural networks. Okay, so we'll try to make this more concrete with a particular example. In order to do that, let's come back to this question. Where do algorithms come from? Well, really, we only have three options, right? So I want to draw an analogy between deep learning and alchemy. So the algorithms might come from the architecture. It might come from the cauldron, okay? Or it might come from the data. the reagents and ingredients that we put inside the cauldron. Or maybe it's the optimizer. Maybe it's the fire we apply to the cauldron to heat it up, or the ladle that we use to move around the ingredients in this cauldron. One of these has to be the answer because it's basically the only thing going on in deep learning. Now, I claim that architecture isn't that important, right? We have many different architectures. They're all kind of good. If I had enough computational resources, I could train any one of these different systems, and I would get a pretty capable model out the other end. The material is not the most important thing. Likewise, I think the optimizer also isn't the most important part of this picture. You know, in analogy with alchemy, there are many different fuels that burn. Sure, coal burns a little bit better than wood. And a Bunsen burner is better than burning coal. You get a more reliable flame. You have some other tricks, like mu parameterization. But at the end of the day, a fire is a fire, right? And if you burn it, your model will learn. You can use many different optimizers to get good performance. So I think at the end of the day, the important thing is the data. That algorithms and neural networks ultimately come from the data you train them on. And we have good reason to believe this. So for example, I can take a single architecture, train it on different data sets, and each time I'll get a very different model at the other end. There's a lot of flexibility built in there. Or I can take different architectures and train them on the same data set. And what you'll find is that often the internal structure ends up looking very similar. So here's a few examples from vision models where different vision models with different architectures converge on similar internal representations for an edge detector. This is convergent property here. Again, so what this is suggesting is that maybe the architecture isn't so important, maybe the optimizer isn't so important, maybe it's the data. And this is true not just for pre-training, it's not just true for when we are making models capable, it's also true for all of the techniques we currently have for aligning AI systems. Right? So instruction fine-tuning. One of the first steps usually when we're training models and preparing them for deployment is you might do instruction fine-tuning on Wikipedia text or some other source of helpful text, just to try to make the helpful personality come to the fore. In RLHF, DPO, and other techniques like this, right? We're just training on a different kind of data set. But all we're doing is substituting the thing inside the cauldron at that moment. And even the kinds of things that people are doing nowadays, where you might use O1 or another reasoning model to generate a very high quality reasoning trace, now you can train against those model completions. So what we're seeing here is that all of the techniques we have for training neural networks, for making them capable, for making them aligned, for teaching them more about a specific domain, all of these look like change the data to elicit different kinds of capabilities and algorithms at the other end. This is the whole game. That's important because if alignment continues to look like changing the data, engineering the data, then we want to know exactly what we're putting in the data and what algorithms are latent, are hidden away in that data. We want to make sure that there are no impurities in the data that could accidentally leak through to the final product. Just like when we're, running a chemical engineering plant, we don't want our reagents to be corrupted with some kind of impurity. So maybe alignment at the end of the day is really a question of engineering the right data distribution for your model. Okay, but we're not done yet. Okay, so how does data give rise to these learned algorithms? Here's a deeper question. What's going on inside of this cauldron? And this is where it starts to get interesting, because it really seems to take place in two steps. So first of all, it's the combination of training data together with the architecture that determines the loss landscape that you end up walking down. It ends up determining the structure of this loss landscape, the geometry of this loss landscape. Where are the mountains? Where are the peaks and valleys? It's this geometry in combination with your optimizer that determines how your model moves around this parameter space during the training process. Okay? How do you learn? How do you move around this space? It's a direct function of these two things. And it's that learning process that at the end of the day determines what algorithms do you learn. This learning process picks out the final choice of weights. So it picks out the final internal structure in your models. So data determines geometry of the loss landscape, determines the structure of the learning process, the sequence of developmental stages, and that determines the final algorithms in the other end. In particular, what we're going to do is this link between geometry and algorithms. It's true for different kinds of learning environments. So it's true for the Bayesian learning process, and it's true for the process of training a neural network with SGD. The thing is, singular learning theory in its current form is a theory of Bayesian statistics. So it tells you about the left-hand side of this figure. Now, what we're hoping to do with this is to use this as a starting point for asking the question we really care about in the end, which is, what kinds of models do you end up with after you train with SGD? In theory, it's easier to study the Bayesian case. In practice, it's easier to do the SGD case. So this is the tension. So what we do is we use SLT to study the Bayesian learning process, and then we can relate this problem to the problem of what kinds of parameters do you actually find using SGD? Okay, so let's come back to data engineering. What I said is that alignment is really a problem of engineering the right data distribution, and that engineering the right data distribution really only has an effect on the model through its effect on the geometry of the loss landscape, and through the effect of that on the learning process. Okay, so maybe we can do more with this. Or maybe we can do more with this relationship. And that's the starting point for a lot of the research that we're doing currently, is asking, are there deeper connections between these different layers? And I want to start by walking you through one example of a connection between these different layers in the form of the local learning coefficient of singular learning theory, lambda. Okay, I'm going to show you how this relationship between these four different levels plays out in terms of this local learning coefficient. So consider data that is simpler. I'm going to take a deep linear network where the problem I'm trying to model is this task. So for trying to predict outputs from a linear transformation of some inputs. And the model I have is parameterized in this way. It includes two matrix multiplications on top of the same inputs. So my learning problem is I'm going to try to find the weights in A and B in order to imitate T. Now here's the thing. If your true distribution is not full rank, for example, if it looks like this, so it's got a 1 in the top left corner, zeros everywhere else, then that means that your model will have additional free parameters. There will be more ways that you can change the weights without actually changing the function. So this shows up in these free parameters here. I can set A equal to this matrix, and that means that in the corresponding B matrix, these two free parameters here, I can set them to any arbitrary value, because when I multiply this out, the zeros will cancel, and 0 times anything, 0. So what you see is that if you are trying to model a problem where the data is somehow simpler, then that often leads to an implementation of your model that has more degeneracy, more ways to vary the parameters without changing the weights, without changing the function. Let me show you another example. We're going to take a ReLU, which is the most common kind of activation function inside of a neural network. If it's the case, and so what this looks like is I'm going to take a matrix multiplication, A times X, your inputs, then I'll run it through the ReLU, which is the maximum of 0, comma, X, and then I do another matrix multiplication. If it's the case that the pre-activations are always negative, well then the corresponding output will always be 0. And I can multiply 0 by any value inside of this matrix to get a 0. So what this means is I would have a free parameter inside of this output matrix. That's true even for a range of values here. So you see that if the data is simpler, if the activations, the pre-activations are always negative, I get this additional free parameter. As soon as I start to actually use this ReLU, so some of the activations are negative, some of them are positive, now this parameter actually matters. It's no longer free. But if I push it even further, and now the pre-activations are always positive, then the nonlinearity will no longer effectively be nonlinear. It'll just act like a linear term. And so this will reduce to the same setting of the deep linear network from before. The simpler models are more degenerate. Okay, so given a data set where the patterns are simpler, you'll end up often with an implementation that is more degenerate. There are more ways you can vary this without changing the function. And in fact, you can actually quantify precisely what this degeneracy is. This degeneracy is measured using the local learning coefficient, which measures the volume scaling rate. So what I'm going to do is I have a toy loss landscape over here. I'm going to take some minimum. I'm going to ask, how many weights are almost as good as this minimum? What volume of weight space can I access within a given tolerance epsilon? In this case, it's the area of the blue surface or this gray surface. How does that change as I change my tolerance? What you find is that this volume scales like some constant times the height, epsilon, to the power lambda, where lambda is the learning coefficient. So the learning coefficient acts like a volume scaling rate. To give some examples, if you have a paraboloid, x squared plus y squared, this will be maximal. So d over 2, the number of dimensions divided by 2, 1 divided by 2, but divided by 2 equals 1. If you have something more interesting, like x to the 4th plus y to the 4th, the learning coefficient will be lower, in this case a half. Or maybe even something like x squared times y to the 4th. It'll be lower still. Now, importantly, if you're looking at the origin here, for these last two cases, at the origin, the second order information is equivalent. So it'll be indistinguishable from the perspective of the Hessian, which is a typical way that people think about basin volume and trying to measure volume. What you see here is that the learning coefficient is actually strictly more informative. It captures more information about the local geometry. Oh. Okay, so as it turns out, the learning coefficient is really the natural measure of model complexity. So for so-called minimally singular models, where every direction is either fully free or it looks like a parabola, the learning coefficient is exactly half the number of effective dimensions. But in more generality, the learning coefficient can also be fractional. Okay, so to come back here, we saw that simpler patterns lead to implementations that you can vary in more ways. And you can quantify this precisely using the learning coefficient. Now, this is important because if a solution occupies more volume, it occupies a larger region of parameter space, then it's easier to find. So it turns out that the Bayesian posterior prefers solutions that occupy a greater volume. And again, you can quantify this precisely using singular learning theory. So the most important contribution to volume is not curvature, it's not Hessian, not the second order information, but it's actually degeneracy. So which direction is going to change without changing the function at all. It's possible to take the problem of Bayesian learning and turn it into a problem of minimizing a certain free energy. So the variational, the free energy we have here is, the details aren't important. What's important is that we've transformed the problem of trying to do a Bayes update into a problem trying to find a minimum of this free energy. We can do because of this reason. In order to minimize this free energy, you have to trade off accuracy, that's the loss term here, L sub n is the loss, against complexity, as given by the learning coefficient. And this trade-off depends on the number of samples you've seen. So if you see more data, then the trade-off can change. In particular, what you see is that we have a data-dependent form of Occam's razor. The model is penalizing complex solutions. If the number of data points that you've seen is very low, then you're going to want to avoid very complex solutions. As you sample more and more data, the linear term will start to dominate the logarithmic term. And therefore, you'll come to favor increasingly complex but more accurate solutions. And what you end up with is this perspective of neural networks as able to do an internal form of model selection, where they automatically trade off complexity to find the right internal model for the problem at hand. Simpler patterns, more degenerate implementations. These implementations are easier to find. They're preferred by the posterior in a way that you can quantify precisely using the free energy formula, which involves the learning coefficient and the loss. What's more, this is related to generalization. So if a model is simpler, then intuitively we expect that simpler models, if they have the same performance, will do better. They will generalize better. All other things being equal, you should go with the simplest solution that explains the data. Again, singular learning theory makes this precise. So singular learning theory shows that you can quantify the generalization error in various ways, probably most importantly through the Bayes generalization error, which looks at a certain kind of at the KL divergence between the true distribution and this predictive distribution, just defined in this way. Predictive distribution is the important quantity in Bayesian inference that you actually use to predict the probability of new samples that you haven't seen yet. And one of the key results from SLT by Professor Watanabe shows that the Bayes generalization error has this asymptotic form where it's given not by the number of parameters, but by the learning coefficient divided by the number of samples, which can in general be much lower. And therefore, you predict that neural networks could generalize much better than you naively would expect from the classical learning theory. And so that shows us a way, very heuristically still, pretty informally, a relation between structure in these different levels, right? So structure in data, in the sense of simplicity of data, leads to changes in the geometry associated to the kinds of solutions you find. Simpler data means more degenerate solutions. Those are easier to find because they occupy a larger volume, and therefore preferred by the posterior, and they generalize better because they're simpler. So all these relations have been made precise through singular learning theory. Now, can we do more than this? I think we can. And so the research bet we have going here, we'll get back to this in a second, is that you can actually do quite a lot more. Now, what I want to explore now is, mindful of the time, we've got a lot to go through, so I'm going to skip over some of these sections. I want to walk through what it looks like to get from here, where we are today, to safe AGI. Okay, and then we'll come back to the actual recent applications of singular learning theory and recent results. Okay, so what is the current plan to make AI safe? Well, the first thing you do is you pre-train on the entire internet. What this step does is it makes your model capable. Next, you have this phase called post-training, in which you do RLHF, RLAIF, a bunch of these techniques that we call alignment. There might be some additional red teaming steps in here where you have a few people explicitly trying to break your system. And then at the very end, maybe there's some additional refusal training where you try to get the model to produce harmful outputs and you train it to say, no, I can't do that. I'm just a language model. So we've got this separation into pre-training for capabilities and post-training for alignment. And then afterwards, all the major labs are now running these dangerous capability evals where they're testing, is my model capable of causing harm? Could it aid in the construction of a bioweapon or some other thing that I really do not want? And then hopefully, if they are actually dangerous, they say, oh, let's wait and not put this on the internet. Now, I don't know if I trust all of the labs to do this, but maybe some of them would. Yeah, there are a few other steps that go in here, but this is the basic process, right? Pre-train, post-train, do some evals. Now, this is very quickly changing. So by the end of this year, we're going to have a bunch of other techniques in this. So on the make it capable side, what you're already seeing from papers like Microsoft's Phi models, there's some DeepSeek models, is that we're becoming much better at curating the pre-training data. So pre-training is breaking apart into multiple stages. We're using existing models to curate data, to select the samples that are particularly informative and easy to learn from. And soon we'll be using, or already, OpenAI is apparently using O1 or O3 to generate training data for its next base model. So we're using the outputs from existing models as inputs to the next generation of models. So we're closing this feedback loop. On the make it align side, I think over the next year, we'll see some of these techniques from scalable oversight actually come online. Techniques like debate and related things. On the make sure it's safe side, we're also getting some new tools. So control evals. So this is, control evals start with the assumption that your model is dangerous and that it wants to do harm and that it's hiding information from you and pretending to be aligned. Can you guarantee that even if it's trying to cause harm, it's unable to cause harm because of the safeguards that you've placed around it? If so, that's the kind of question that control eval tries to answer. And I think it's quite likely that we'll also have the very first interpretability-based evals or maybe understanding-based evals. You train a sparse autoencoder on your model, and you can inspect these features and try to find maybe harmful directions or directions associated with lying. Maybe you can make sure that those values never exceed some critical threshold. So very quickly, we're starting to flesh out additional things here. Now, what happens next? Well, I think more and more, the distinction between pre-training and post-training is going to vanish. So I think you're already seeing that, right? Because of the way that O1 feeds back into the training process. But I think soon we'll have something where you're pre-training with reward models already in the loop. You're designing careful curricula of synthetic data to train your model in the right order and the right time. And maybe you're already doing RL kinds of things from the very start. So that this distinction between pre-training and post-training breaks down. And that's a little worrying to me. I was worrying for a few reasons. Right? So we talked about these earlier. The problem is that we do not know how to reliably make much more capable systems aligned with human values. And back when we were in this scenario where we have this distinction between pre-training and post-training, maybe it's relatively easy to analyze the capabilities. But as soon as they get mixed in this awful way, well, I don't know how far off distribution we can end up. And I have the sense that this is a more vulnerable position than we are currently, that we're going to need deeper kinds of alignment techniques in order to make this go right. Okay, I'm going to jump ahead to the last section just because of the time. If you're interested in any of these, you can ask me about it or email me or ask a question in the follow-ups. We'll jump ahead to the last section. Okay. Okay, so we saw this picture of this relationship between data, geometry, learning, and algorithms. And we saw this example of the learning coefficient as an example from singular learning theory that shows this relationship. Now I want to show you an empirical example of the relationship between these kinds of levels, these different levels, as developed in really a series of 2 papers that I worked on with some collaborators over the last year. So what we did is we looked at small 2-layer attention-only transformers to start out with. And what you find here is, if you look at the loss, that's the top plot, right, the loss goes down pretty smoothly over all of training. So you don't see anything particularly interesting. But if you look at this local learning coefficient, then you find this stage-wise learning behavior, where there are these plateaus that seem to split the training process into different stages. Now, what you can do is you can draw a vertical line at these points and try to cut it up into stages and ask, is this meaningful? Does this actually mean something? And what you find is that, yes, in fact, the stage identification process that you've done in this way yields something meaningful. First, your model learns bigrams. Then it learns a number of n-grams and skip n-grams. Then it starts to learn previous token heads. It finishes forming what's called this induction circuit, and finally converges to something stable. So by looking at this local learning coefficient over the course of training, we can, in an unsupervised way, before knowing exactly what these changes mean, automatically differentiate these different developmental stages. Okay, so what we see here is a link between statistical patterns in the data, bigrams, skip n-grams, n-grams, induction patterns, and the structure of development, the order in which the model learns these different things, from simple to more complex. At the same time, we see this reflected in the shape of the curve of the local learning coefficient over the course of training. And we see it in the structure of the critical points of this curve. They reflect the barriers between these developmental stages. In a follow-up paper, we looked at what we call the refined local learning coefficient. The one thing you can do with the local learning coefficient is you can do what's called a weight refinement. I freeze most of the weights and look at the learning coefficient of a subset of weights, maybe an attention head, or maybe some other part of the model. What you get is these curves like you see here. So each of the lines here corresponds to a single attention head in the same model. The other thing you can do is you can do what's called a data refinement, where you change the data set you evaluate this on. What you'll see is, so all of these curves will change in shape, right? Because it's a different data set, so it has different kinds of behavior. Okay, so what does this give you? What can you extract from this kind of tool? Well, first of all, weight refinement reveals differentiation of heads over training. So it reveals that the heads are actually grouped into clusters that correspond to different kinds of capabilities. So what you see here is we're looking at the layer 1 heads. You see that the heads are clustered into these groups where the clusters are actually meaningful. So the simplest heads with the lowest complexity score learn the most algorithmic structure. They learn what are called induction heads. The next most complicated heads are what are called deque heads, which are involved in nested parenthesis matching. So if you open up a bracket and then you open up a parenthesis, and then you want to open up a quotation mark, you have to close the quotation mark before you can close the parentheses. Okay. And then as you go up to the next heads, you'll find that the heads memorize more and more information. So what we're seeing here is a link between this refined learning coefficient and the complexity and the amount of memorization taking place in these models. Okay, so additionally, the data refined learning coefficient reveals specialization of heads over training. So looking at this, I'm going to go kind of through it at a faster pace. You see the important figures here, that these two heads jump out above all the other heads. And these two heads turn out to be a very special kind of attention head called an induction head. And there's a separation between them. So 1.6 seems to be more important here than 1.7 is. This is on the GitHub dataset on code. And what you find is that, in fact, 1.6 seems to be specialized to punctuation in the kinds of tokens that show up especially in GitHub data. So you can not only detect clusters of heads, but what kinds of data they specialize to. And lastly, we use this to discover a new kind of circuit, which we call the multigram circuit. And jump over this. So to complete this picture, what you find here is that in terms of algorithmic structure, you can actually use these refined learning coefficients to detect different kinds of attention heads. And you see that in the geometry associated to these different heads. You can even use it to study higher level algorithmic structure like circuits, again, reflected in patterns of geometry and how it changes over the course of training. So we're starting to flesh out this correspondence, right? More ways of relating structure in these different levels. So almost there. I'm going to go over time just a little bit, but we'll leave some time for questions. Our underlying vision for this research agenda is something that was articulated by Daniel Murphy, one of my collaborators at the University of Melbourne, building on the ideas developed by Sumio Watanabe and other collaborators. And it's something he calls the S4 correspondence. So maybe there's a deeper way to link these different things. Because in mathematics, we have many different ways of talking about structure in data. Statisticians talk about correlation functions, sufficient statistics, a bunch of other ways of talking about what structure looks like in data. If you talk to somebody who does algebraic geometry, they have many different ways of talking about geometric structure. Talk about resolution of singularities, talk about jet schemes, talk about many other words that I don't fully understand. If you talk to a developmental biologist or somebody who studies dynamical systems, they'll talk about things like developmental stages, phase transitions, bifurcations, catastrophes, maybe mixing times. These are different ways of talking about structure in some dynamical process. If you talk to a computer scientist, they'll talk about structure of algorithms in terms of features and circuits, control flow, iteration, memory management, subroutines, this kind of language. So maybe in the tradition of many great mathematical endeavors, it's possible to actually develop equivalences between structure in these different layers, right? Isomorphisms between structure in the one and structure in the next. And there'll be a series of papers coming out from Daniel Murphy and his students and collaborators that starts to flesh out these relationships between structure in these different ways. And at the same time, we're trying to also turn this into a set of empirical tools that we can use to actually probe structure in large learning machines. Okay, now let's come back to the very last bit, which is, what does this mean for safety? And what can we do for safety now? Right, so here are a set of 3 directions that we're pursuing where we hope to use this relationship to have an impact on safety in the near term. First, I think there are applications for evals, questions around data. So for example, what even are capabilities and values? Is it possible to use a better understanding of structure in the data to design more efficient evals so that I only have to run a limited number of tests in order to actually establish what my model is capable of? Can I use this understanding to develop scaling laws for specific capabilities instead of just overall general performance? We're working on a number of projects in this direction. What about interpretability, right? Understanding these final algorithms. Well, there are a bunch of techniques that we're trying to develop that build on ideas like the refined learning coefficient that look at more fine-grained structure. Can you go from the structure of an entire intention head to structure of individual weights, measure certain kinds of correlations between them? There are other very interesting quantities in SLT, like the singular fluctuation. Can we use this as a basis to develop new kinds of techniques for interpretability? And ultimately, the question I really want to answer, and that I think a better theory of singular learning theory can contribute to, is what is alignment? What is machine learning? How do we choose data in a way that we actually end up with the algorithms we want on the other side? And I think those kinds of questions are questions we can start to answer with the theoretical framework of SLT and the set of tools that we're developing on top of this. So we're not there yet, right? We got a lot to do, but maybe we see a path forward to answering some of these difficult questions in alignment and AI safety. With that, I would like to thank you very much and leave some time for questions. Thank you.
Thank you so much. Thank you so much. That was a great talk showing how well Jesse Hoogland connects singular learning theory with AI safety, AI alignment. And the part about the future of self-AGI development, especially in the second half, felt very fresh to me and interesting to me. They're living here in Tokyo, far from San Francisco, Berkeley. Thank you very much again. Yes, and
Thank you for having me.
yeah, that was a truly excellent talk, great talk. I'm very impressed. Yes, so interesting talk. Does anyone have any questions? Have Jesse Hoogland? Feel free ask English or Japanese. もしジェシー・フーグランさんに ご質問があればぜひお願いします。山川さん、はい。
I'm Hiroshi Yamakawa, member of the Line. And I'm very impressed. I'm not sure about the singular learning theory until now, but I'm very understand it is related to self AI. But I'd like to more concrete example. Could you highlight 2 or 3 key scenario? What SLT specifically contribute to the AI safety? For each scenario, so could you explain something SLT provide theoretical guarantee or ideally some kind of concrete example? So could you explain some example where safety related?
Yeah, so I'll give an example of some projects we're working on right now. So one project is relevant to what's called weight exfiltration risk. So a lot of the policies at scaling labs assumes that you can keep the model weight safe, right? That an adversary isn't going to steal the weights somehow. One of the ways to make sure that this happens is to enforce a rate limit so that you cannot leak more than, say, X number of gigabytes within some narrow time window. And so what that relies on is that your rate limit is tight enough that you can't leak out the entire model within that window. But the problem is that models are very compressible. Right? You can often throw out many parameters after training them, and so maybe the naive weight limit, the naive rate limit, isn't enough. You actually have to make it much smaller than you naively would think. There's a perspective from singular learning theory on the minimum description length principle that extends this to account for neural networks and singular models that could give you theoretical guarantees, lower bounds on how compressible a given model is. And therefore would tell you, oh, as long as my rate limit is below this, it's not possible, it's theoretically guaranteed that I can't exfiltrate my weights. I can't free my weights from this data center.
Yeah, thank you very much. But anyway, that SLT to applying the AI safety is now very much in progress. It's a situation. Is it a correct understanding?
Yeah, so this is a project we're working on. I mean, it's not being enforced yet, but this could lead to recommendations for labs and certain kinds of things you could measure.
Thank you very much. Yeah, okay.
Does anyone have questions? Any questions?
I have a question.
Yes, please.
Well, first of all, thanks for the talk. It was really interesting. Not familiar with singular learning theory in the past, but I really want to learn more about it now. There was one comment you made. It's not directly related to the concept of singular learning theory, but you were highlighting, how we do alignment now versus how we might be moving towards doing it in future. Could you go back to that slide for a second? Would that be? Yeah. Yes, it's further than I recalled. Yeah, here. So you mentioned that we were moving away from this paradigm where we first make it capable and then make it aligned towards a paradigm where we're sort of doing those two things in a single pass at once. And you mentioned that this seems risky because of the kind of shallowness of our alignment techniques as they exist now, as you discussed earlier in the talk. I was a little surprised to hear you describe it this way, because it seems to me that, at least this is my intuition, that the shallowness of our current alignment techniques may depend in large part on the fact that they are only applied, at the end.
Yes, I think this is totally right. Yeah.
So I would think if anything, this would be the opposite. This would make our alignment deeper by weaving it into the entire training process. Would you disagree with that?
I think it's like whatever values you end up with, yes, it makes deeper. Is what I think of this process. But I think it's
see.
also more likely that if you get it wrong, that it will lead to to more significant divergence
I see.
from our intentions. And that's
It would be
basically
harder to
because
correct an initial misalignment in this stage.
yeah, that's
I
because I'm afraid of RL. Reinforcement learning is just right. It's like the only thing that's reliably produced super intelligent systems, AlphaGo, and various game playing agents that are really, really beyond human ability and everything.
Mhm.
Yeah, and I just worry about the way things go off distribution when you train them in an RL kind of setting.
I see. Okay. That makes sense. Thank you.
Thank you so much. Yes, does anyone have any questions? Oh,
Yeah, actually,
yes,
thanks
please,
for the
please,
talk.
please.
Yeah, so maybe this is kind of like a bit in the weeds, but I was wondering like if there is like a small data set of like sort of a complex concepts like subject matter expert classifications. From what you've said, like is this sort of thing where like a larger model that's just like should overtraining on this should do better, or a smaller model that's like kind of I'm not really sure. Like I guess it's not clear to me like what we should predict the performance to be like based on this sort of mixture of like not much data on a complex concept.
Yeah, I'm not sure either. I think this is also to some extent just an empirical question. To highlight another kind of impact I can imagine for SLT, when we're evaluating models, one of the main problems is that all of the labs are gaming benchmarks. They're testing against all the benchmarks, so maybe the score that they report isn't actually real, it's not actually meaningful or informative. So we would like to measure ways. We would like to measure how much is your model actually memorizing this data versus generalizing on it. And the learning coefficient gives us one way to gain additional information about this and to distinguish maybe one model that has memorized it perfectly versus another model that has actually learned to generalize correctly on some data set. So I think you could use this empirically to start testing this question.
Oh, is it make sense? The answer for your question? Okay, yeah, thank you. And I found one question that from Naoki Hayashi. The typical application of singular learning theory is model selection, such as WAIC. Do you think it is possible to utilize evaluations based on LLC not only for generalization performance, but also for selecting models in terms of safety?
I think most questions in safety are questions about generalization. Like you've measured performance on some training data. You want to know, is it going to continue performing in the same way on this data? Is it going to continue being safe on same data from the same distribution? So I think because of that, I think this is exactly the reason that I'm optimistic about applying it to deeper problems in alignment, is because of this connection to generalization. So yes, although I don't think in practice, the way I think this looks I don't think it looks like train 10 different models and then run the model selection procedure at the end and compare them and then choose the safest one. I think you need this procedure to be all throughout the learning process where it's guiding the selection of safer models.
Okay, I got it. Is it make sense, the Naoki? Yes. If possible, please type your answer in chat box. Yeah. Unfortunately, yes. Okay, I got it. The time is up, and I really enjoyed and impressed the Jesse Hoogland's great talk. Thank you so much again. Yes.
ありがとうございました。
もうありがとうございました。超楽しみました。Super impressed. Yes.
Thank you very much.
Yes. So, and
Thank you very much.
yeah, today's webinar is closing, and unfortunately, but thank you so much attending today's webinar. Yes, thank you so much again. Goodbye, everyone.
Goodbye.
青柳先生。
Oh,
Hi, nice to see you again. Thank you very much for your nice lecture. See
Thank
you
you.
soon. See you.
See you soon.
Thank you. Sorry.
Thank you.
Sorry.
青柳先生、ありがとうござい
いえ、
ます。
こちらこそ、あ
うん
りがとうございます。すいません。ちょっと、なんかこう話そうと思いながら、すいません。こんなになんか、
じゃあ
すいません。
もしよかったら、ぜひ質問いただけると。
So thank you very much for your excellent lecture. It was very interesting. So also, you spoke about weighted LLC, right? No?
Oh, you the weight? Yeah.
Yeah. So if possible, but I think it's time short. But if possible, can you could you explain the weighted LLC more detail?
Yeah. So so what I'll do is I have a model and I've trained it and I have some weights.
Mhm.
So what I'm going to do is I will freeze most of the weights.
Mhm.
And then I am going to estimate the learning coefficient of a subset of the weights. So I'll use stochastic gradient Langevin dynamics
Mhm.
to move the weights around to derive my estimate
Mhm.
for a new model, where the new model has the parameters changing in just that subset of weights.
Okay. So, okay.
I'll send you the paper afterwards,
Okay,
and you can
okay.
read the definition.
Okay. Thank you very much. Thank
Yeah.
you.
Thank you.
Yes, yes, that's a very excellent, the great talk again. Yes, thank you so much again, the Jesse Hoogland. Yes, I'm glad to hear today. Yeah, you were
Have a
very,
great rest of your day,
yes,
and until soon. See you
yes,
soon.
yes. Okay, then bye bye everyone. This is the end of the webinar. Today's webinar talk. Thank you so much again. Bye
Thank
bye.
you.
See you
Thank
soon.
you.
Bye. Bye.
ありがとうございました、青柳先生。
どうもすいません。突然。
本当に嬉しかったです。どうもありがとうございまし
いえ、本当にありがとうございました。
た。本当に。はい。では、終わろうと思います。
はい
じゃあ、皆さん、本当に今日はありがとうございました。
失礼いた
失礼し
します。
ます。